Okay, we're going to start the next unit of material, which is quantum physics. This is basically just going to be an overview of what we would call modern physics, which is physics that has been discovered in the last century and a half or so. And it diverts from what you've learned about physics up to now because it looks at differences from what we understand about the atomic level of stuff to what we understand in classical physics. So part of the problem with the classical model, one big problem was when we started looking at light. So that's why we put this unit after we talk about light. We knew about these things called black bodies, which are objects that absorb all the radiation that hits them, and they re-radiate at the temperature they are. So think about your car in the summertime. If you park it out in the sun, it's absorbing all the sunlight, and then when you get in it, it feels very hot. So it's absorbing mostly visible light and some ultraviolet light and some infrared light. But what you're feeling is infrared. You're feeling the heat of the steering wheel or the seat or whatever. So that would be an example of what a black body does. It absorbs all this energy and then it re-radiates at its particular temperature wavelength. So black bodies were described in two ways. The first way they were described was by what wavelength they peaked at, and that's found through Wien's law. And Wien's law says that as the temperature of the black body increases, as it gets hotter, the peak wavelength gets smaller. Think about a burner on an electric stove, okay? You turn the burner on and the first thing you feel is the heat of that burner. So that's infrared. Then you see it start to glow kind of a dull red, and then it's a brighter red, and then it's an orange. And if it kept getting hotter, then it would be yellow, and then it would be all these different, go through the spectrum. All right, think about it like in chemistry, you want that blue Bunsen burner flame because it's hotter than the red flame. Okay, so what happened is the other thing that describes a black body is called the Stefan-Boltzmann law, and that describes how intense radiation is from it, so how bright. And what the Stefan-Boltzmann law said is as the temperature increased, the brightness increased by the fourth power. Or excuse me, as the temperature increased, you took the temperature and you took it to the fourth power, and that told you the brightness. So that's a better way to say that. So in other words, as the temperature goes up, things get really bright really fast. The problem with that is if you assumed, like the classical model had up to now, that if something's giving off a certain energy, it gives off all the energies up to that point equally, and you calculated that, then essentially it was giving off this incredibly huge amount of energy that was essentially infinite when it got to ultraviolet wavelengths. In other words, when it got so hot that it would be emitting in the ultraviolet, then it should give off so much energy that it basically exploded or it was destroyed. And we know that's not true. So they call this very colorfully the ultraviolet catastrophe. And so what Max Planck said was this means that the emission cannot be happening equally at all wavelengths. All right, so that energy has to be compartmentalized, or he called it quantized, based on that particular object's chemical makeup. So Max Planck developed this idea that energy is quantized into these discrete values so that different elements or different compounds or molecules had their own distinct packages of energy that they emitted, but they didn't emit at all wavelengths of energy. And what he ultimately concluded, or what was ultimately concluded, he didn't do this, but what was ultimately concluded was this was related to what we call the atomic oscillations, or the electrons in those atoms giving off energy based on their excitation value. So an excited atom, or think about what you learn in chemistry about these suborbitals, like the subshells, moving around in those subshells, those have distinct energy values that are unique to that element. So Einstein comes along with this concept called the photoelectric effect. The photoelectric effect we use all the time now for solar panels. The The photoelectric effect says when light hits a target, if it's the right energy light, in other words, if it has the right frequency, then it will eject electrons from that target. But one photon gets you one electron. So let's say you send in a photon that's got more energy than you need to eject the electron. The electron doesn't just take the little piece that it needs and leaves the extra for something else. It takes it all. It's quantized. It gets that whole packet of energy. So what that means is the electron is ejected with some extra energy. If you get a photon that comes in that's twice the energy that you need, you still just get one photon. It's just got a lot of extra kinetic energy. So one photon gives you one electron means that light and matter were interacting together, which was a new concept, and that they kind of had similar properties when they did that. So that was a new idea, that energy and matter were linked. Okay, so if you wanted more electrons, you didn't need higher energy light, you just needed more light. You needed more photons, a brighter light. Okay, you could still have the same low energy wavelength, the same color, if you will, of light. You just needed brighter light. So you got more photons, which gave you more electrons. But you had to meet that minimum energy that you needed. That's called the threshold frequency or the cutoff frequency. And that's determined by what metal you use for the target. Every metal has something called its work function. If you don't meet that work function, that's the minimum energy that you need to eject those electrons. You're just shining a light on a piece of metal. You're not ejecting any photoelectrons, okay? You're not ejecting any current. So this little cartoon kind of shows that, all right? If the light frequency is too low, there's no current flow. You turn it up to the right threshold frequency, you see some electrons. If you want more electrons, you need a brighter light, okay? So notice those purple squiggles in the second and third picture have the same number of squiggles. It's just one's taller than the other, indicating a higher intensity. Okay, so this is unique to the material. It's something you have to look up when you are using these materials. Now, another thing that happened to kind of go along with this concept that Max Planck came up with was something called the Bohr model of hydrogen. Okay. Up to now, people weren't sure what the structure of the interior of the atom looked like. They thought maybe it was like a mini solar system, or maybe some people thought it was more like, they called it a plum pudding, okay, where there was this diffuse charge, kind of like the pudding, and then the electrons were kind of stuck in there like the plums, or I think of it as chocolate chip cookies. You've got the cookie dough, which is your charged, positive charge, and then your negatively charged electrons are stuck in there, okay? So Bohr proposed this concept of the mini solar system, where you had the nucleus in the center. In this case of hydrogen, it's a single proton with the electron orbiting around it. Now, his model, as you'll see in next week's lab, wasn't completely right, all right? The solar system model wasn't completely right. There's more going on there, but it was a good place to start because it gave us the option of quantizing the energy levels. What it meant is the electron could have more than one orbit that it's circled at, and this is where we get into these subshells that you might talk about in a chemistry class. But since the nucleus and the electrons in the orbit have different interaction based on Coulomb's law, like from Unit 2, different elements are going to have different levels, or I call them stair steps, different stair steps that they need to reach that all have different energy values. So I can take the unique set of energy values for that particular atom, and I can identify what that element is. So what this does is it lets us talk about the different types of spectrum. Okay, so what happens is when you shine light on a sample of gas, say you shine a continuous spectrum light on a sample of gas, a couple of things happen. One of the things that can happen is that gas will absorb its particular stair-step energy values. It won't absorb all the light. It'll just absorb those unique values that it needs to excite its electrons, because those are the only ones that do it any good. Then once that gas heats up, it will emit those values, those same values in an emission spectrum. Okay, So as the electrons are excited up, you get an absorption spectrum because they absorb that energy and then they re-emit that energy as they decay back down. Now, it's not always as simple as you go up one level, you jump back down, okay? Let's say you had an electron that jumped from its ground state, which we call n equals 1, the principal quantum number, up to n equals 4. Now it's got to go back to 1. So how much ever energy it jumped or it absorbed to jump up to here, it's got to give you back. So the way it can do that is it can jump all at once and give you everything back at once, or it could go 4 to 3, 3 to 2, 2 to 1, and you get 3 different photons for each jump. They're a lot lower energy, but when you add up their total energy, it adds up to the amount to go between 1 and 4. Or it could go 4, 3, 3, 1, or 4, 2, 2, 1. In all the cases, the total energy has to stay constant. So the more jumps you make, the lower the energy of each individual photon. Okay, so that's why even though hydrogen only has 1 electron, it has a complicated spectrum because it has a lot of different ways that it can jump between these levels and get back to where it started. All right, so the Balmer series is the series we think of when we talk about for hydrogen. It's the one that's visible. It's one that's in the visible light range. It's actually where the electron started out at n equals 2 because maybe the n equals 1 shell was full, all right, or that's where it began, was n equals 2, or maybe we don't worry about n equals 2 to n equals 1. So you look at anything that lands at n equals 2 is a Balmer series line, okay? Now, the first 4 are visible lines. So H alpha, H beta, gamma, delta. Those are visible lines. So that's why we know those well. All right. But there are other lines in the ultraviolet and there are lines in the infrared. Anything going down to n equals 1 has so much energy, it's actually an ultraviolet line. It's called the Lyman series. And then there are series that are lower energy that go to n equals 3 or n equals 4 that are less energetic and they're infrared. Now, some states are metastable, which means most of the time when you're jumping back and forth between these energy levels, the time that it hangs out in the excited state is really short, like a millionth of a second. Okay, so what that means is it's usually cascading back down as another one is getting kicked up. So there's this jumping back and forth, okay, between these levels. But sometimes that excited state has a lifetime that's maybe tenths of a second or seconds, and we call that a metastable state. And so what you can actually do is you can get a sample of gas that has what's called a population inversion. It has more electrons in that excited state than it has atoms with electrons in the ground state. Then a couple of things can happen. The first thing is, if you have something that glows in the dark, that's because it's full of a material that has excited electrons that are gradually cascading back down over the course of time. So the light from the sun or your lamp or whatever is exciting them up to this metastable state. And then over the course of time, they'll gradually decay down because these lifetimes are an average. The average might be a second, but some of them might stay there for an hour or 5 hours, and some might go in a millionth of a second. It's an average value. So over the course of the night, those electrons would cascade back down and make that thing glow in the dark. The other thing that this controls is lasers. Lasers are where you get a population inversion and then you force a big cascade all at once and it gives you a big burst of energy. Okay, so that's the whole point of a laser. We call it pumping to push those things up into the metastable state, and then we hit them with energy and they cascade down rapidly and all at once. They give us a burst of energy. So with a laser, you have to have enough of a sample that you can have this cascade, but you still have others being pumped up there. So you have a lot of atoms going back and forth, but you bump them down in a big bulk amount, basically. So what this does is it gives us this concept of wave-particle duality, where particles, matter, and waves, energy, have some common characteristics. And this was a breakthrough of quantum mechanics. So quantum mechanics broke the rules of classical mechanics, all the stuff we've learned about in physics 1 and 2 up to now. but it had its own set of rules that were consistent for things of very small scale. So atomic size things, elemental size things, nuclear size things, very small scales. So sometimes particles act like waves. So there's times where electrons will act like they have a wave function, and there's times where light acts like a particle, as in the photoelectric effect. So some properties of this are tunneling. Tunneling is how our modern electronic world works. Tunneling means that the electron, when you talk about in chemistry class, you go to the electron cloud model, and the cloud is really a cloud of probable locations. It's sort of a spread of where this electron might be. So what tunneling is that probability cloud sometimes puts the electron outside the atom, or sometimes it puts it inside the nucleus. And that may be a very small probability that's there, maybe 1 in a billion that it's there, or 1 in a trillion. But when you've got Avogadro's number of atoms, which is 10 to the 23rd, 1 in a trillion is still 10 to the 11th electrons that are able to make that jump outside the atom. Okay, so tunneling is not really like, you're digging along like in Minecraft, okay? It is literally the probability function sometimes makes that electron appear outside the atom. And then that's how all computer chips work. They rely on this electron's probability to bump it out of the atom and bump it over into this other material and cause electrical current without there actually being a direct contact there. The probability, or the wave function of the electron, or the wave behavior, is measured by something called the de Broglie wavelength. The de Broglie wavelength measures the waves of matter. So all matter has a de Broglie wavelength. We have one. It's just so tiny we don't notice it. Okay, it's 10 to the minus 34 for normal size stuff. So we never exhibit wave-like behavior. But when you get down to electrons and things in the nucleus and things in the atom, then the wavelengths become like 10 to the minus 6, which is light. Okay, so we can measure that. Photoelectric effect we already mentioned was an example, and then the quantization of energy levels we also mentioned. So these are all examples of wave particle duality. So this is where I'm going to stop this particular set of notes, and we'll come back and do some more.